Hi everybody, and welcome to Climate Change Calculated Part 4. My name is Gerald Schuller. So it's a little bit since last time, so first a little recap. I find it fascinating that many sometimes controversial questions about climate change can be answered independently with the physics of the 10th grade in school and open data, something that's openly available in the internet. I spent a lot of time and effort last summer and autumn in calculating key issues of climate change, and it indeed worked. So that's the fun part. Physics has the advantage that everything can be checked independently using data and mathematics, and that's particularly important in times of unfiltered mass information and sometimes misleading information and political propaganda. So this time we want to answer the question, what can we do? So let's continue with the recap. In part one, we answered the question, does mankind cause the observed increase in the atmospheric CO2 concentration through the use of fossil fuels? And the physics we found out clearly says yes. We saw that if fossil CO2 emissions were to be stopped today, it would still take about 150 years, so roughly 150 years, order of magnitude, before pre-industrial CO2 concentrations were reached again. Right? So this shows the inertia in the system, that it takes some centuries before it basically goes back to the pre-industrial level. Only at that time, global temperature would stop rising. So up to this point, it would actually accumulate more and more warmth, heat in the atmosphere. In part two, we answered the question, does the increase in the CO2 concentration cause an increase in the global temperature? So this link between CO2 and heat. And the physics we found clearly says yes. Basically, this is the spectral absorption of CO2, which causes the greenhouse effect. So if the CO2 emissions remain the same, the CO2 concentration will continue to rise and the temperature rise will correspondingly be faster. So that's the problem. We already have a high level of emissions, and this high level already causes a continuous increase. And the more we emit, the faster this increase will go and the faster the temperature will rise. And that's the main problem that we have. So in part two, we saw that the global temperature is now already over 1 degree above the pre-industrial value. So it's already significant. It's already higher than basically eternities before. So in part three, we answered the question, does the increase in CO2 concentration cause the poles to melt and cause a significant rise in the sea level? Right, and we also found physics says yes. So here we use simple physics of the heat capacity of water and the melting capacity of ice to find the sea level rise. So in part three, we saw that the global economy is also very sensitive even to local disasters such as floods. We found that hard drive production, for instance, was impacted for years after a flood in Thailand. So in that context, there were civilizations before that were causing caused or intensified regional climate change. Right? Sometimes they caused, sometimes they just intensified climate change, and they vanished as the consequence. They couldn't adapt. So it's a lesson that we can learn from the past. And examples are the Nazca culture or the Indus culture in India. And they caused this mainly through deforestation and also unsustainable irrigation. Yeah, basically that led to these civilizations to vanish. Yeah, so the goal of keeping global warming below 2 degrees Celsius or even 1.5 degrees Celsius is still realistic and technically feasible, which I will show here. But it requires global measures as shown in the Paris Climate Agreement. So they have an important path forward, and this shows basically also a path to the solution. And this should be done quickly because we could be close to tipping points where it would be taking much longer time to go back to pre-industrial levels if we go above those tipping points. And all this can be calculated with school physics. So that's basically the fun part of it. It's actually not so difficult. It's actually quite easy to calculate. Yeah, interestingly enough, this physical observation has become a political issue, even though it's basically simple. Much like the physical observation in the 17th century that the Earth revolves around the Sun was controversial, and not the other way around, which the Church insisted for fear of losing power and influence. So it was at that time also a political issue. Then the church was fearing for losing influence and power, and nowadays it's the fossil fuel industries and industries which rely on fossil fuels, which are fearing for their business and influence. So politically quite similar to the 17th century, but over the long time you cannot deny physics because that's reality, right? Yeah, so I will now show the feasibility and um, how to limit global warming in the following. So fossil CO2 is actually just a form of air pollution, and this can be solved in similar ways as previous pollution problems, not with restrictions, but with technical solutions. So this actually gives us hope, right? It's actually not as difficult as it might seem, although it is difficult, but it's possible. So examples, for instance, are garbage cans in Paris around 1700. At that time, um, Paris grew a lot, became more populous, and they had problems with the garbage. Everybody was just throwing it onto the street. And they were introducing garbage cans to collect trash. But even that was met with resistance because it involved effort and cost. Right? So here you can actually read more about it. Then later, catalytic converters in cars in the 1980s. And with the introduction of unleaded gasoline, the air became indeed much cleaner, was successfully improved, and also the forest health was improved, which can be read here in this Wikipedia link. So that was actually quite a good measure, useful and it helped, but it also demanded new cars, which were also a bit more expensive, usually a few $1,000, similar to electric cars today, which are also a few $1,000s more expensive than the gasoline ones, and also against which the industry at the time also resisted because they were afraid of their business, right? But because of the new laws, catalytic converters became cheaper and standard, and prices fell because of the production volume. So this is an example of successful policies to improve a common good, which is the air in the cities and the forests, right? So this worked. In the end, everybody was happy, and cars actually became not really more expensive because of this measure. Next example is a worldwide ban on CFCs as coolants and propellants and their replacement with alternatives. Right? So this is for refrigerators, for instance, or air conditioners. This was in the 1990s, and this successfully reduced the hole in the ozone layer. So ozone layer is actually since then closing, and it's almost as good as in earlier times now. So this was actually quite a good success. And this was actually also a good example for a worldwide cooperation. So within a few years, countries agreed on a worldwide ban on those CFCs, and it worked. And maybe it was successful because it was done in a short time frame before political resistance could develop. So nowadays it's accepted, and it's also no business problem. Then later we had this ban on low power light bulbs in Australia and Europe and also the US, which was not strictly enforced, but it promoted the switch to LED lamps. And as the result, the number of units rose, so many more LEDs were produced, and as a result, prices fell a lot. And now LEDs are in price comparable to earlier light bulbs, but they have many more advantages, like much less energy consumption and also lifespans of decades instead of just a year. So this is then our principle of getting away from fossil CO2. We just have to avoid fossil energy altogether, like CFCs, right? We just have to avoid fossil energy. In principle, it's that simple. Oil, coal, and gas must remain in the earth. Nuclear energy does not produce fossil CO2, but it is not really practical or economically in the long term because it is not renewable. So it only has limited resources, like oil, so it lasts only for a limited time. And in principle, it also generates unlimited costs for storage of spent nuclear fuel. Right? So this fuel needs to be securely stored for millennia, and this basically means we have unknown and basically unlimited cost. And this becomes apparent now that the first nuclear plants needs to be disassembled. So we have nuclear waste there. And also we don't have any finite final resting place for the spent nuclear fuel. So it's still an unsolved problem with in principle unlimited cost. So that's something that no company would like to take on. So on contrasting that to the energy from renewable sources, which is actually now cheaper. It's actually among the cheapest sources of energy, as we will see in a moment. What also helps is strengthening nature to reduce fossil CO2, for instance, to avoid large-scale deforestation of forest. So this helps nature to absorb CO2. So we can switch to technology that do not use fossil energy. So this technology is already there. We just have to use it. So there is technology that uses electricity as a form of energy. So instead of gasoline or oil, we just have to use electricity, which comes from renewable sources. So it's important that the electricity is not already completely from renewable sources, but that our technology is ready to use electricity from renewable sources in the future. So this means that CO2 balances should not be based on today's electricity mix, but on the future electricity mix so that we can plan. So this mix will hopefully do without any fossil CO2 in order to see how sustainable technologies are for the future. So now let's take a look at what proportion of electricity is already from fossil fuel sources or fossil sources in general. And for that I look at the electricity in Germany in 2019. And I have the numbers from this link here. So there we can see that the renewables already are at 46% of the electricity. So you have to think about it. The electricity produced in Germany already comes about half from renewable sources, which for Germany is 236 terawatt hours. The rest comes from non-renewables like lignite, nuclear energy, natural gas, hard coal. But these make up a much smaller part. So you can see each is below 20%. So the biggest share is already renewables. So that's important to know. So we're already halfway there. So this is the remaining share. And this remaining share is already comparable to the renewable energy that we already have. And this means it's doable, right? We just have to do it again. And then we're there. So then the questions, can we replace these renewable energies? Is it affordable, right? And now we can take a look at the cost, the production cost or generation cost per kilowatt hour. So this includes costs for construction, operation, dismantling, repair of a plant, divided by the lifetime energy generated in kilowatt hours. So here we have a price comparison from the Fraunhofer Institute. So we can actually click on this link here. So here you can see a nice picture where you can see the different energy sources and its price range. So here on the right, a wide range is gas. So it ranges from medium to high. Here we have biogas. We can see biogas is already somewhat lower than standard gas. And then we have several renewable sources. Like this is photovoltaic from the roof. So roof installations, this is the free installations on like acres. This is wind onshore, wind turbines onshore. Here's wind offshore. And here we have as a comparison coal, lignite, brown coal. Here the stone coal. So this shows the coal and lignite are actually already on the same level with photovoltaic and wind. So that shows that those renewable sources with production prices already compete with current cheapest production from coal. So this actually gives us a good business case for investing in renewable instead of fossil fuels. So back to the slides. Similar to for nuclear energy. So when we look at the economics of nuclear energy, I found an interesting link here from 2009 already. So we can actually click on this one here. So here we can see a report from Citibank. And you cannot say that Citibank is particularly green. They're actually the ones who would fund building new reactors, and they say it's not paying. It's not worthwhile. The economics say no, because it's too expensive to build and produce electricity using nuclear energy. And here I have another link for the comparison of different fuel sources or power sources, this time in English. So here you can also see a list when you scroll down. So here's a list, US dollars per megawatt hour. So you have to scale it by a factor of 1,000 to compare it with kilowatt hours. And here you basically obtain quite similar numbers that I just showed from the Fraunhofer Institute in Germany. Yeah, so these numbers I summarized here in this little list. So solar energy, we have a range between 3.8 to 6.5 cents per kilowatt hours and falling over time, so they are getting cheaper. Same for wind onshore, 4 to 8 cents per kilowatt hour, decreasing. Gas, 10 to 22 cents per kilowatt hour, more or less constant. Lignite, 4.5 to 8 cents per kilowatt hour, but increasing. And if the damage caused by climate change and the eternity costs would be included, we would have considerably more cost. So this also means the cost will be increasing. Nuclear energy, we have at least 6.5 cents per kilowatt hour and increasing. So this was 2009. I have 100 point for 2013 for the new reactor in Great Britain, Hinkley Point. They get 11 cents per kilowatt hour. So this already shows that it's increasing. So if the cost for final storage and accidents, similar to liability insurance, would be included, we would have considerably higher prices. So these costs are now mainly borne by the taxpayer. So these are hidden costs, basically subsidies by the taxpayer. So in conclusion, renewable energy is already the cheapest form of electricity. And gas can replace nuclear power and fossil energy for the transition simply because there are already many gas generators, which are used for backup. But what can we do individually? So let's take a look at what we can do as an individual. So first, we can simply book a green electricity tariff from renewable energy where available. So in Germany, we have many of those tariffs where we can actually book a purely renewable energy plan. And it turns out that they are not more expensive. Sometimes they are even cheaper than the standard plan. So also economically, it makes sense to switch to renewables, not just for the environment. And in the future, when we have more CO2 pricing, the difference will become even bigger, right? Then in comparison, the renewable tariffs will become comparably even cheaper. And this also has the advantage that the demand for renewable energy will generate a corresponding supply. So energy companies will have an incentive to build more renewable plants. Yeah, then the next is transport. We can see that we only use electrical energy for transport if at all possible. So this means electric trains, electric trams, electric buses, also electric cars or car sharing with electric cars. Electric cars are now already there. They are still pretty new, but available and practical and not even that much more expensive. And since these will be the future, it makes sense to now only buy electric cars instead of gasoline cars. And they will also last longer because they have more longer lasting parts like electric motors and batteries. Turns out they are lasting much longer than gasoline cars with their high pressures and high temperatures. Yeah, if possible, do not use cars with combustion engines with fossil fuels. Because with fossil fuels, there's no way we can reduce the fossil CO2 output much. Or also avoid trains with diesel engines or diesel buses. Same thing. They will always emit fossil CO2. Wherever possible, use a bike or walk, right? That's also healthy. Or if it's if we have to use fossil CO2, like when traveling by air, we can still buy CO2 offsets. Right? This is not perfect, but it creates demand for climate-friendly projects. For instance, afforestation, to have more trees which then absorb more CO2 from the atmosphere. Yeah, and use only renewable energy for the household if possible. So use heat pumps as heating, or if possible, set up solar energy on the roof of the house, or a small turbine if possible. So this is particularly interesting for the winter time when there's a small wind turbine to generate electricity. Yeah, and important for for the renewable energies, is the development of key technologies over time. Particularly important is this price drop of lithium-ion batteries. So, which can be seen here in this link. This is this German Statista link. You can see a nice graph, which I can open now. So here you can see the price of lithium-ion batteries per kilowatt hour over time. So on the left you can see 2013 we have a price of 400 euros per kilowatt hour, and in 2019 it's already just above 100, and it's predicted that this year it will become below 100 euros per kilowatt hour. So you can see it's a factor of more than 4 of the price decrease within the last 7 years. So that's substantial. Yeah, so price has dropped to less than 1/4 in just 7 years. And this is important because it will make renewable energy baseload capable, which means we have batteries for the night or for the winter time, or when there's not much wind blowing. These lithium-ion batteries can be used to buffer those loads. And that's essential. Yeah, then we can take a look at the wind power, the development of the average nominal power per wind turbine. So here's the German Wikipedia link, and there you can see in 1990 we had an average power of 164 kilowatts. And 2011, so it's already 9 years ago, but even at that time we had an average of 2.2 megawatts. So that's a factor of more than 10 in just 20 years. So it's also significant. Similar for solar cells. When we look at the solar cell efficiencies, here I have the English Wikipedia webpage. We can see that in the 1980s, where the first solar cells were available, we had an efficiency of about 5%, which means 5% of the energy coming from the sun shining on this solar cell is converted into electricity. Then fast forward to 2020, and nowadays commercially available solar cells have an efficiency of approximately 20%, and research cells over 30%. And that's already comparable to the efficiency of chlorophyll in plant leaves. So about as good as nature is doing it. So basically this is probably as good as we can get it. And this means we have an efficiency increase by a factor of 4 over 40 years. So that also makes it quite practical for residential power supply. That means 10 square meter of solar cells will deliver about 2 kilowatt peak power at our latitudes, meaning latitudes of Germany, which gives us about 2000 kilowatt hours energy over the year. So that's also for Germany. So if we assume we have some kind of battery storage, then this is enough for a one-person household. Right? So if you have 10 square meters, which is not enough, which is not much. That's basically the roof of a carport. So the roof of a carport would deliver enough electricity over the year for a one-person household. So if we have storage, then we could become independent of the electricity grid. So that's kind of amazing, I think. Also, the installation cost fell by more than half during the last 10 years, which can be seen here in this link. So this means that solar cells, if we have the possibility to install it on our roof, is already cheaper than regular electricity. And the increase in efficiency make it realistic to generate the required electricity. These technologies are also an important driver of current and future economic growth. So developing new solar cells, new wind turbines, electricity storage, maybe smart grids to control the electricity flow. This basically creates a new market. And this is also a chance to position ourselves as technology leader. So they're also more environmentally friendly to build and dismantle than coal or nuclear power. So when you compare it to coal, we have all those landscapes, escapes with which are scarred by digging coal, or even underground. When we have mines underground, then it just takes time for the ground to sink over time, and that creates problems for buildings that are built on it. So that creates a lot of trouble for the future. And also nuclear power, as I mentioned. Even dismantling a nuclear power plant takes decades and billions of dollars. Contrast that with wind power, for instance. It's very easy to dismantle and it leaves almost no footprint. Similar for solar cells. You can easily dismantle them and they leave almost no footprint. So there's almost no cost for dismantling them. So more on this and on calculating how the switch to 100% renewable energy is possible then in my next episode. So thanks for your attention and like my channel and then see you next time. Bye bye.